Welcome everyone to the second day of our tool training on performance-based engineering application that we developed. This day we'll dive deeper into how this performance-based engineering app works and what possibilities are there. So I call it the advanced damage and loss assessment details. Before we start, I would like to do a short recap. I promise it's going to be very short. About yesterday, for those who were not able to join us and didn't have a chance to look at the video. I included a slide here at the very beginning that helps you set up your environment and run the tool. All of these slides are available at DesignSafe, and I encourage you to download them if you have not done that already. Matt already reminded everyone about the message board that we have. Please go and check it out, and we appreciate your feedback. We really do want to hear what you think. We are not only listening to positive feedback, so if you have a negative opinion, please let us know that as well. Yesterday, we looked at the user interface of the tool. I walked you through the different steps that you need to perform a basic loss assessment. We looked at the HAZUS and the FEMA P58 style assessment. And then I also showed you where the results are saved and how to import external EDP data. I showed you the process of importing that data. I did not go into the details of how that data needs to be formatted. So we will talk a little bit about that today. But before that, there are two things I want to point out related to yesterday that I learned during the office hours. One of them is that this ground motion tool does not always work, apparently. It seems to be related to an issue with USGS. I don't want to blame them or anything, so it's not that, but it could be the way we connect to them, but it's definitely a connection issue. So this part of our tool is kind of mercurial. Sometimes it works, sometimes it doesn't. If it doesn't work, I suggest you to switch to the stochastic ground motion like this. So you change the event, and then you can do the examples just the same way, because our examples are not focused on the actual results you get, but it's more about the experience of running the tool. So if the USGS option doesn't work, switch to the stochastic ground motion, and then you can run the examples just the same. Make sure you do not provide a seed value here, because if you do, all the ground motions are going to be the same, and that's not really reflecting the uncertainty in the hazard. Another problem that I learned yesterday is that this prescribed value is not loaded appropriately. Everything else is populated fine from the input file. This is the only value that is not. I'm sorry about that. So when you load the input file, make sure you put a 0.0 here to let the analysis run properly. Okay, that's it. Everything else should work fine. So for those of you who tried to run this yesterday and were not successful, I apologize. And thank you for those who came to the office hours and let us know about these issues. All right, so today we have a lot of things to discuss. There are many modeling options in the PBE app. I'm not going to be able to show you all of them. So I picked the ones that I thought are interesting for the largest number of people. And I hope that you will find this valuable in your research in the near future. So these are the topics that I'm going to cover. We will start with EDP inputs. I will look at the format of that file that you can load in. And then we will look at how those samples are used and resampled in the background, in our background Pelicun engine. What are the options for resampling and how do we handle collapses? There are multiple options available for handling collapses. Then we will talk a little bit about residual drifts and irreparability, which is a connected concept in FEMA P58, which will be followed by the performance model. That's a very important part of the P58 loss assessment. You will see that that's also quite a time-consuming part of defining the loss model. And then finally, I will show you a couple of details about calculating injuries and estimating repair time and the limitations of these in our current software. So let's start with EDP inputs. Yesterday, I showed you that you can load external responses from a CSV file by putting the file path here. And when you specify a file here, we skip everything else that comes before and go straight to loss assessment. So that leads to a faster analysis and allows you to use, let's say, results from ETABS or SAP or even OpenSeas, but your own MATLAB script in this tool. Now let's take a look at how this file looks like and what are the standard formatting requirements to make it work in the PBE tool. This is the file from yesterday. It's in the example folder. Oh, by the way, I didn't mention, there are no new examples for today. I'm using the example files from yesterday throughout the demos today. So this response CSV is available in yesterday's example zip file, and I skipped the beginning of the file with a couple of other columns that show random variables that were generated. That's not necessary for the damage and loss assessment. So to do the damage and loss assessment, what you need is a file that is structured like this. You have an index column where each row will correspond to one simulation result. So this is 20 ground motions, so 20 simulations, as you can see. And then a header, which will identify the various EDPs that came out of your simulation. Each column is going to be corresponding to one EDP. And we have the following naming convention. This is quite important. So it starts with a number, then it has a 3-letter identifier of the type of EDP that you collected. Then we have an identifier for the location and another one for the direction. This event ID might be puzzling. It's gonna be one for almost everyone. We are preparing for the time when we will run multiple events that are happening consecutively. Think about fire following earthquake or an aftershock after the main shock. In such cases, you might have one for the main shock and 2 for the aftershock. But in most of your research, I believe you are running a single event. So this is going to be 1. I will talk about the EDP types in a second. The location is where you measure this EDP. In a building, this is typically the floor number. So you are going from 1 to the number of floors when it comes to story drifts, or you are going from 0 to the number of floors when you are talking about accelerations or velocities, for example. The direction is not X and Y, it's also numbers. This gives you more flexibility. You don't need to have 1 correspond to the horizontal direction and 2 to the other horizontal direction. You can have an arbitrary number of directions on each floor. The typical convention that we use is that we assign 1 to the X and 2 to the Y, but this is up to you. I will explain how this has to be in sync with the fragility descriptions that you use so that our engine is able to pick up which EDPs to pair with which fragility functions. Okay, I have 2 examples here that you can look at that shows what 1PFA01 and 1PID22 means. Now, which types of EDPs do we support? That's also an important detail. We support quite a few already. So besides the typical peak interstory drift and peak floor acceleration, we also support peak floor velocities, residual drifts, peak roof drifts, and a couple of intensity measures also. So if you want to use fragility descriptions that are based on intensity measures rather than engineering demand parameters, you can do that. You just need to provide the intensity measures as if they were EDPs and provide the right fragility descriptions, and then everything else is taken care of in the background. If you need other types of EDPs, you can easily extend Pelicun, the backend, to understand those EDPs. I will show that tomorrow. And then you can use even the PBE tool to use those EDPs and do the loss assessment with them. One more important detail about the EDPs before we go on is the unit that you use to populate these tables or this table. You can see that the acceleration values, this is peak floor acceleration, are provided in the same unit that we have selected in the general information tab in the application. I told you this yesterday, that this decision that you make here is quite important, and it's important to stick to it in every step. So if you have inches there, then the accelerations are expected in inches per second square. If you have meter, then of course it's meters per second square, and so on. So make sure that you use the right unit here. When it comes to drifts, you don't have to worry about that because drifts are unitless. All right, so this is how we can import the EDPs. And now let's see what is happening with those samples in the background and what are the different options that we have. So I'm talking about these parts of the input panel. We have a response description part, detection limits, collapse probability, and collapse limits. Now let me first show you a couple of figures to explain why do we go beyond just fitting a log normal distribution as it is described in FEMA P58. So I have a quick one-dimensional example here. Let's say we are looking at a peak interstory drift at a particular story. Let's say the story that drives the building performance. So say the first story in a soft story building. And this is a histogram of a number of results that we have. So say we ran 50 simulations, and this is the distribution of the drifts from the 50 simulations of a particular building. This result could correspond to a relatively mild or moderate earthquake. And as we increase the intensity of the earthquake, we will get larger and larger drift values. And what you need to recognize is already here, when we are around like 5 or 6% median interstory drift, here at the 20% value, we have something that is strange. This doesn't really seem like following a log normal distribution, right? So we have results that follow a log normal distribution. These are synthetic results, so it's just to demonstrate the problem. And then here we have something that is different. And if we keep increasing the earthquake intensity, then we might have something that looks like this. And I'm pretty sure you are familiar with what's happening here. It's quite typical that people have a cutoff drift value where they terminate the analysis. So if the model that they are using reaches that drift, they consider the building collapsed. And then instead of actually calculating all the way and then getting a result that is higher than 20%, the results will show 20% there. If we do not consider this in the post-processing step, then we would fit a log normal distribution on this type of data. And you can imagine that this would kind of lead to a biased result, and our mean value would be actually lower than if we had the actual values beyond this properly represented. So one thing that we can introduce here is a collapse limit, where we can provide the value that we used in the analysis and that we want to consider as the limiting drift or floor acceleration or any other EDP. And if the results in the samples that we provide are beyond this collapse limit, then those simulations are considered collapse in the post-processing and in the loss assessment phases. So the collapse limit is to consider this type of data collection. Then the other feature, the detection limit, considers that there might be a value of drift. In this case, I said it's 10%, beyond which we do not trust the nonlinear model that much. And depending on where the collapse limit is, this might be important. If the collapse limit is rather far, so say you specify a 50% drift as the as the collapse limit, but you have results between 10% and 50%, I think it's hard to argue that your drifts at like 30% will be just as accurate as those around 5%. So with the detection limit, you can specify this threshold beyond which we do consider the results, but we believe that their actual point is not that important. And what we are doing is we consider it as censored data and calculate what is the fraction of all results that falls into this area, and fit the distribution to make sure that the probability mass in this area matches the fraction of the results that are here. But we are not trying to force to match at this point or the exact point of the result that came out of the analysis. So this can be a powerful tool when you have a lot of results in this range, which happens usually when you reach a couple of dozens of percentages of collapse probability. So here, if you look at this one, for example, we are looking at only 8% probability of collapse if we believe that this is accurate. Okay, so this is detection and collapse limits. Now, let me show you how this works if we keep increasing the EDPs. So from here, we went up to about 30% probability of collapse. And now you see that if we did not consider the collapse limit, we would get a completely false estimate for the log normal distribution. And you can also see that because our numerical model is less reliable above this limit, even this part of the histogram does not follow a log normal distribution. So as I mentioned, by having a detection limit, when we fit the log normal distribution, we try to follow the histogram until this point, and then we make sure that this part has the right amount of probability mass in it, and everything else is cut off as collapse cases. We can specify if we want to fit considering the collapsed cases and then censoring for the whole remaining part, or fit only for non-collapsed samples and then considering collapsed cases separately. So then we will get a distribution that is conditioned on no collapse. I will show you how to do that in a second in the application. The last thing I wanted to mention is the difference between fitting a log normal distribution and a truncated log normal distribution. When you fit a log normal distribution, its range is going to be from 0 to infinity, right? The problem with that is apparent in this case. So I created this other data set where I imagined that I trust my numerical model because we are only ranging from 0 to like 10% drift. But for some reason, in this structure, the collapse limit is at a much lower value. So it's around 8 or 7% drift. This comes from an example. For example, I used buckling restraint braced frames. The braces are going to fracture quite soon. Some people argue that much sooner than 8% drift. So there's no reason to run the analysis for further. And then you have a collapse limit here, but you have a distribution that looks like log normal until that point. Now let's zoom into this part to show you how that looks like. So it's the same thing, I just zoomed in to give you a better sense of the shape of this distribution. If you fit a log normal distribution to this data, even if you consider this as censored data, so you don't try to force the distribution to make this jump here, but you only want to make sure that the probability mass is accurate, even then you are going to have a problem because you will have this distribution, you will sample it during the loss assessment, and you will get values in this range. So the distribution conditioned on no collapse is going to provide you EDPs that are beyond the collapse limit. And I believe that's problematic. So what you can do is you fit a truncated distribution, which we automatically truncate at the collapse limit. And we make sure that all the EDPs that are generated during the loss assessment are going to be below the collapse limit. So this way you can make sure that you are indeed sampling EDPs that are conditioned properly on no collapse. Now, let me jump to the application and show you how this looks like in the tool. So I've just started it. We opened the same example from yesterday, this P58 assessment. I'm not going to run the analysis because this is much more about how you set it up than clicking the run and seeing some results, I believe. So we can choose the response.csv file. This way we load in the results of a response estimation. And then what I described in the previous slides is how you can choose between log normal or truncated log normal. I will mention the empirical in a second. If you choose all results, that means you consider the collapsed cases as well when fitting the distribution. Or if you choose non-collapsed results, then you will have this condition on no collapse. And your analysis will be, all your results will be conditioned on no collapse in that case. The detection limits are provided here for interstory drift and for floor acceleration. I have not received requests for other EDPs. If you do have other needs, I can extend this further or I can make it more flexible. So there's no, this is not by any means limited to these two EDP types. Collapse limits are here, same thing, interstory drift and floor acceleration. And then the collapse probability needs to match your settings in the response description part. So for example, if you say that you want truncated log normal with non-collapse results, this is what I showed in the last slide, then you would either prescribe a 0 probability of collapse, which means that all your results are going to be conditioned on no collapse and you will need to calculate the losses from collapse cases separately, or you can prescribe a particular value here, say 5% probability of collapse. And then in the background, we will calculate the collapsed cases based on the prescribed value and the non-collapsed cases based on the truncated log normal distribution. If you say that you want to use a log normal distribution with all results, so you believe that that log normal distribution is going to handle your collapsed cases appropriately and describe those large EDPs appropriately, you can decide to have an estimated collapse probability. In this case, the prescribed value is not required, and you can choose to estimate the collapse probability based on the sampled EDPs. So that means we take the data here, fit a log normal distribution, you provide a value here, say 8% interstory drift, and then we calculate the probability of the interstory drift being larger than 8% based on the distribution that we fit to the data. And that's going to give the probability of collapse for that analysis. You can also choose to use the row EDPs, which means we are not using the fit here. We take the raw data that you provide and check how many of the data points are above this 8% or whatever you provide here. So, and there's one more option, yes. If you say empirical, that means we are not doing any fitting. Take the data that you provide and use it as is. This is very powerful if you have your own approach or your own method to post-process your response estimation data. So say you have 20 samples, but you want to use a different distribution. You want to use some other considerations to fit that distribution. You can do it outside of the PBE app. Then you can resample outside of the PBE app and just make sure that if you have 5,000 realizations here, then you provide 5,000 samples in the response file or decrease this number accordingly. Those samples are going to go through the analysis as is, and then you can use them for collapse estimation, or you can still provide a prescribed value for the probability of collapse. So I believe this is very powerful and flexible. You can do several different approaches to EDP resampling and collapse estimation with this. Give it a try and let me know how it works, and let me know if it doesn't work for some reason. Now, let me go back to the presentation and continue with the residual drifts and the irreparability. It's a little bit related to what we discussed in the last few minutes. First, we will need to have an understanding of what residual drifts are used for. Irreparability is driven, or the decision on irreparability is driven by the residual drift in the building. So if the building is not straight after the earthquake, if its residual drifts exceed a certain value, then it's considered not repairable and a total loss. So this can have a huge influence on the loss results in some cases. Again, buckling, restrained braced frames are one example, which tend to have large residual drifts. So you want to be careful with these settings, and you want to know how they work when you run these assessments. The capacity part is quite straightforward. It's described in the FEMA P58 document as a log normal distribution. We take that log normal distribution approach here. You can provide the median and the logarithmic standard deviation of that distribution, and we will sample that to get the capacity for each realization of the loss assessment. The interesting part, or the more difficult part, I would say, is the demand side of the equation. You have three options here in the PBE tool to handle the demand. The first one is that you run a simulation and you collect the residual interstory drift values from the simulation, and you provide them here as either external data or internally. You have a user-defined EDP, and then you collect those values from your simulation. The problem with this could be if you have zero residual drifts. This can happen, for example, if you have a relatively mild earthquake, so the structure does not yield, then the drift is going to be zero. The problem with the zero case is that it's very hard to fit a log normal distribution to zero values. So you will have to figure out something to avoid having those zeros. You can decide to remove them from your samples, but then you will remove the cases with small drifts, so you will overestimate the residual drift demand. You can also decide to replace them with a small number, whatever that small number is, but having those small numbers in the log normal distribution will overestimate the standard deviation. So again, you will have some bias in your demand. So this is not necessarily a good idea, or depending on your structure, depending on how sensitive it is to residual drift, this might be an important bias that you put in the analysis. So the other option is that you use what's described in FEMA P58 as an approximate method to estimate the residual drift values based on the peak interstory drift values. This is automatically performed by the backend application of PBE. So you don't need to worry about the details, but you can check them here. You need to provide a yield drift ratio, and then as long as you have peak interstory drift values, we calculate the residual drifts during the analysis. The advantage of this is that you don't need to fit a distribution for the residual drifts, so we can afford having zeros in there. The disadvantage of this approach, besides the topic of is it accurate enough, I don't want to get into that debate, but even if we accept it as accurate, the problem is not going to be applicable to every building type. And you might be looking at a special type of a building that is not covered by what's provided in FEMA and the relevant literature. And then it's very hard to use this approach for estimating drifts. So there's a third option that is the most flexible, which is you can bring your own drift values and use an empirical distribution here. So rather than asking PBE to fit a log normal distribution to your samples, you can do the fitting or the resampling or whatever approach you believe is the most appropriate for residual drifts outside of the PBE application and provide the samples that you got from that process and ask us to use them as empirical data. This way, you can be sure that the correct or the distribution that you desire is used in the loss assessment, and the residual drifts are calculated and the irreparability is calculated appropriately. Okay, let me go on and look at the performance model next. This is this components tab in the P58 in the PBE application. And rather than showing slides, I will actually show the application now because there are a couple of settings that are better seen in action, I believe. So if we go to the components tab, you can see that we have two parts here, a component ensemble and a component details part. The ensemble is our database or the available set of components. If this field is empty, that means we are using the default database, which is what is provided in the second edition of FEMA P58. This is about 750 different components that were prepared and created as part of the P58 or ATC 58 project. It's important that we are using the second edition, so that's recently released data. All of those components are available in the list here by ID number. If you don't know what they are, which can happen, then you can simply say that you want to add all of them, and then you will have them among the selected components and review their details. Whichever component you select here is going to be described below. So this B1035.041 is actually a pre-Northridge beam cannon join. And then you can walk along this list by the cursor buttons and see what each component is. You can remove one or you can remove all of them to prepare your performance model. Now, adding components here is not sufficient to have them included in the analysis. This is just collecting the fragility groups that you would like to use. But according to P58 methodology, having a fragility group is one step, and then assigning it to specific parts of the building and creating performance groups with quantities identified is the next step that is required to be able to calculate the losses. So what we do is, after adding a component, we need to add the component group as well. Let me add a new component just to demonstrate this kind of randomly. So we have this 1041 here. That's how it looks like, nothing here so far. And then we can add the component group by clicking here. And we will need to specify the location, which is basically the floor, the direction, which is the direction of the EDP that is controlling the damage in this component, the quantity and the unit for that quantity. You are not limited to using the quantities in FEMA P58. Some of those have strange units like 30 square feet. I believe it's easier to think about square feet and then provide the actual value. So you don't have to say this is 10 times 30 square feet. You can say 300 square feet, and I do the math in the background. In this case, it's actually quite easy because this is a each. So you don't have to do that kind of unit transformation. And then for distribution and COV, this is allowing you to have uncertainty about the quantity of the component in the building, in that performance group that you provide here. You can have normal or log normal distribution. The N over A means that you are sure about the amount of components, so there is no uncertainty. For normal and log normal, you can provide a coefficient of variation that describes how much uncertainty you have about the quantities. One important detail here is that some components are non-directional, especially the ones that are controlled by acceleration. Let me add one of those, kind of randomly, so I hope it will work. Excellent. So this is a non-directional component, meaning either direction of accelerations can drive the damage in this one. So when we add a component group, you shouldn't worry about adding 1 or 2 as the directions. You can just keep it 1. And in the background, we will take the governing acceleration in the given floor. So say floor number 2 to estimate the damage in these components. When it's directional, say, in this case, you do have to specify the directions that you want these components to be applied in. So in this example, we have these pre-Northridge beam column joints. What this line means, we apply it to all floors. So this is a 3-story building. So that means we apply it to 1, 2, and 3. That's 3 performance groups already. We apply it in 2 directions. That makes it 6 performance groups. And in each performance group, we will have 2 groups of components, 4 and 4 pieces in each group. So this means we have 6 groups with 8 pieces total in each group across the building. This takes some time, I believe, to wrap your head around it. It's a very compact way to define performance groups in the building. If it doesn't make sense, or if you think there's a better way to do this, I'm very interested in how to improve on it. This panel improved quite a bit over the last, say, 2 years, and I am interested in your ideas and opinions about how it works for you. One thing that you have not seen yet is that you can add more of these. So if, say, you have 4 of these connections, or 2 times 4, in one direction, but in the other direction you have 6, what you would want to do is you say, this goes to the other direction, and now we have 2 times 6 each. So this identifies that the 2 directions are different. The number of components is different in one direction than in the other, but they all belong to the same fragility group. And then if you say that in the first floor you have different numbers, you could put 2 to 3 here, and you could put 1 here. Let's say they are the same in the 2 directions. Let's say they are 8. The idea behind having multiple groups here is to control the correlation between damages within a performance group. So if you see that these have independent behavior, that means that the damages are not correlated. So it's very important to identify how many groups of components have similar damages within a floor. You can break it down to, say, instead of 4, you could have 1, 2, 3, 4. That means all 4 of these will have their damages evaluated independently. If you put 4, that means these 4 will have similar damages. Now, this makes perhaps a bit more sense when you look at something like partition walls. So here we can say there's 150 linear feet that we consider as one unit. And altogether there's 450 linear feet in a performance group, but the 3 pieces can have damages evaluated separately. And you can see that in this case, we have some uncertainty about their amount on each floor. Okay, now, although I believe this is a powerful tool for prescribing component groups and components, I understand that when you have 50 different components and you want to have an overview of how that looks like, there are better ways to do it. So Another option that we provide is to save this setup in a CSV file and load it back in after you modified it in an external tool or just in Excel. I'm going to show you how that works. So we have added a couple of components. We have 5 different components here. I will save it to a file. Let's say in this folder, just like that. And then I go to that folder. You can see the file here, but rather than opening it directly by double clicking on it, I will pull up Excel and load it as data. I will stop here for a second. So in the data tab, get data from file CSV. The reason I do it this way is that if you load it just like a regular file by double clicking on it, Excel tries to be smart and replaces some of the number ranges with dates. And those are very hard to turn back into ranges of numbers. So it's better to open it as data, and then it will be much easier to work with. You can see that Excel will parse it. Just click load. And here it is. So these 2 to 3 ranges would become probably February the 3rd. It will happen here again if you do it like this. Oh, March. Yes, the 2nd of March. So this is unfortunate. And what you can do is you select this column and just change the format to text. And then it will not try to override what you are saying. So now, just to show you how this works, we have this extra component that we added. I'm going to put it to the 2nd and 3rd floor, direction 1. I don't remember what, I think it was each. And let's say normal distribution 0.25. So you can edit this. You can even add new components if you know the ID for them. And then as soon as you are ready, you just save it as a modified version. Like this. Perhaps I don't need to put this here. Yeah. I'm not sure it saved it well, but let's see. And then you can load it like this. And when we go to this extra component, you can see the data that we provided in the Excel file. So it's a very easy way to export and import data and edit the data, perhaps share with others, and then load it back in for the analysis. It's also efficient when you have different buildings, say buildings with different heights, and you want to use the same performance model. You notice that I can put all here, that puts it to all floors. So I don't need to worry about how tall the building is. Those components will always be assigned to every floor. And then maybe you have a separate thing on the 1st floor, so you have those as like this, or maybe you have something else on the roof. You can have roof here, and it will allow you to assign things to the roof without knowing actually how tall the building is. Okay, so this is about the performance model. Another detail that I wanted to show you is how we handle damage and loss data. And although we use the default data from FEMA P58, oftentimes you want to go beyond that. If I pick the first component here, you will see why. So I add this, you look at the first component, and you immediately see this incomplete data here. If you see something like that, that's a red flag. That means that in FEMA P58 or in PACT, this component has some missing data. So we cannot run the loss assessment using this component. If you add such components to your assessment, they are going to be skipped. So it will not fail, but it will not be included in the assessment. Now, what you can do is you can export the default database, look at the component data, and add the missing values. I didn't do that myself because about 30% of the 750 components have missing values. And sometimes it requires research or at least a literature review, to come up with data that is missing there. So it's not a mistake made by the creators of FEMA P58, it's just reflecting the state of the art at the moment. What you can do here is click on Export Default Database. You need to select the location for that. We will select this folder. By the way, this is an important detail. Those who are using the Windows version of the tool will not be able to do this with yesterday's version of the tool, because unfortunately one file is missing from the distribution. So we have updated the zip file on DesignSafe, and if you would like to test this feature, please download that file again and overwrite what you have used yesterday. I apologize for that. The Macintosh users were more lucky. The file is not missing in their package. So I selected the location, and then I pull up that folder, and you can see that we have a data directory and the population file here. In the data directory, you can see that every component has a corresponding JSON file. And if we open one of these JSON files, like this, then let's open this one. This was the one that we looked at in the tool. You can see that it's incomplete. But first of all, you can see that this is human readable. It's a structured file that describes the fragility and the consequence functions of this particular component. You can see the quantities, you can see if it's directional, you can see the EDPs that are used for the component. And then from here, you can see the damage states, 1, 2, 3 damage states. Okay, for each damage state, we have fragility curve details and then consequences, red tag, reconstruction cost, reconstruction time. If there are injuries related to the component, those are also appearing here. Now you see that this is incomplete. If we look at another one, this 2011, that's a good example. That's why I wanted to bring that up. 2011-201A. This one being incomplete, you need to look for undefined as a text in this file. Whatever is missing will have this undefined flag on it. So for this component, we have the fragility undefined. This is very unfortunate. Oftentimes the reconstruction cost is undefined, which is easier to correct, I believe. But this one is hard to come up with unless you do literature review. But now let's just say that we come up with some value here, 0.4, and say that it's false. So it's no longer incomplete. Save it, go back to the tool. And now we can choose that we want to use an external database. So the data that we have just exported here, select that folder. And if I add that B2011-201A, it's no longer incomplete. Just to show you how this works, I add its pair, which we did not correct, and it's still incomplete. So this way, you can go here, check the components that you would like to use, check those that are incomplete, and complete the data, pull in that folder, and you can use it immediately in your assessment. Okay, I think I will skip the injuries if there are questions, and I will save them for tomorrow, because if you do have questions about the first 4 parts, I think it's more important to answer them now. If there are no questions, I can still talk about these last few slides. So Matt, please let me know if there are questions that I should answer.
Yeah, thank you, Adam, for these lots of details in this tool. A couple of questions.
Okay.
I guess one is pretty basic. The units that are defined in the model and in comparison with the units that you're showing in the damage and loss consequence functions. If you select SI units or you select imperial units, are your damage and loss and components then in the same units that you chose for your model?
So if I understand correctly, the question is about the units that I specify here versus the units that I have here. Do you agree, Matt? Okay, so this part, the components part, the units there are completely independent from the units of the EDPs. So these units influence the engineering demand parameters and how they are handled when you either load them from here or you get them through the analysis. The units inside the performance model are decoupled from that, and I have an interface that makes sure that they are matching the ones that we have in the EDPs when it's important. When it comes to quantities, these are absolutely independent from EDPs. They don't even have to match. So I guess the short answer is whatever you provide here does not influence what you provide here as a unit.
Okay, thank you for the clarification. The next question is a little bit, it goes back to the truncated distributions. So how do you define a truncated distribution? Is it by defining the detection and collapse limits?
Yeah, so when you select the truncated distribution here, you do not define the distribution parameters, you just define the format, right? So you say that you would like a PBE to fit a multivariate truncated log normal distribution on your sample data. The only thing that is required there is the truncation point, and that's going to be the collapse limit that you provide. So in each dimension of the EDPs, it will be truncated at the limit that you have here. If you don't have any limit for floor accelerations, for example, that means it will be truncated in the drift dimensions and it's not going to be truncated in the acceleration dimensions. I hope that makes sense.
Okay. And I think probably our final question is, do you maintain the correlation of EDPs in the different demand generations? So this is the
yes. Yes.
And as a follow-up, is there any source to learn more about the theory of these models?
Well, I guess most of them. So I think this the log normal case and the sensor distributions are covered in the literature for sure. The truncated case, I cannot point to a paper just like that, so it might be my idea. I'm not sure, but I think if there's nothing in the literature so far, then there will be a paper very soon that describes this by me and some other people at SimCenter. So until then, you know, if someone is interested about this, send me an email or write something on the message board, and I'm very happy to discuss the details. Or if you feel that there is something wrong with this approach, I'm also interested in that.
Okay, so I think those are all the questions we have for today.
Okay.
Would you like to proceed, Adam, or
yeah, I think I would, because this is a rather short last few slides. I just wanted to make sure that that we have time for questions. So I just wanted to touch on injuries and repair time, because usually we focus on repair costs and how that works in the basic examples. And there are a couple of details about injuries that are important to know. So when it comes to injuries, we want to know first, we want to be able to specify the peak population, how many people are in the building. There are two ways to do that in the PBE tool. You can either provide a single value, and then that value will be considered as the building population, so it's distributed across stories in a 3-story case, which means that you will have 10 people on each floor. You can also provide a list of values if you say that you know that the number of people are not evenly distributed across the floors, and you can do it like this. Another detail with, related to injuries is the population model. So how is the population changing over the course of the day? This depends on the type of occupancy and is described in FEMA P58. We use those descriptions to come up with a population JSON file. This file is saved when you export the database to this external folder here, just to give you a quick look. So we have the data folder and we also have this population JSON file. This file already has the FEMA P58 data in it. Now you can extend it by adding a different occupancy type instead of elementary school, something else here. And then you can change the population distribution accordingly if that's something you're interested in. Or if you want to turn off this feature, you want to use the peak population. For all of the realizations, you can just put 1.0 everywhere, and then we will not model the changes in the number of people. Finally, I'm trying to switch slides. Yeah, the collapse modes are another important detail when it comes to estimating the number of injuries. So we had the general tab and the components. So far, we looked at these two. The collapse modes are the third tab. And here you can add as many collapse modes as you wish. I have an example here having a complete and a partial collapse mode. You need to have a collectively exhaustive set of probabilities assigned to these modes. So this setup means, for example, that we have a 10% probability of a complete collapse and a 90% probability of a partial collapse. For each collapse mode, you need to specify the affected area. A complete collapse affects, for example, the full floor area, while in the partial collapse, I assign different floor areas along the height of the building. Again, we have the same approach that I showed you with the population. If you have one number, it's applied to every floor. If you have a list of numbers, then you can specify different areas for each floor. The last part is the proportion of people getting injured or passing away due to this type of collapse. So in this case, we say 80% of the people will have injuries in the affected area, 60% of them will be casualties, and 20% will be fatalities. And likewise, these numbers work for partial collapse. Okay, so this is very important to consider if you do want to simulate collapses. If you prescribe a 0% probability of collapse, so you are essentially learning a non-collapse analysis, then this is not needed. This is not going to have an effect on your results. And the last thing I wanted to mention is related to the replacement time. This tool so far, unfortunately, is limited to what's described in FEMA P58. When it comes to FEMA P58, it provides a great way to estimate the replacement time for each performance group in the building, but there is no methodology for the sequencing of repairs that would give us a reasonable estimate of the total replacement time or repair time, sorry, for the building. So what happens is that we can either assume a parallel replacement or repair of each performance group. That's going to give us the shortest possible time, or we can assume a sequential one, which gives us the longest possible time. It's important that since the second edition of FEMA P58, this time is expressed in worker days. So these are not days, these are worker days here. If you look at the two values, the parallel and the sequential repair times, you can see that the sequential ones are much higher. Basically, these two values are giving you the lower and upper bounds of the repair times. These bounds are often so far from each other, especially when you add more components. This is a small analysis with only 3 components. This sequential time can often exceed tens of thousands of worker days, while this one is still a couple thousand worker days. So we understand that this is not enough, and we are working on including methods for sequencing. One of the methods that is very often used is REDI, developed by ERAP. We are talking to them and we are trying to have that in this tool. There are other methods by researchers that are also looking very good. So if you have your own method and you wouldn't mind having it available here, then talk to us. I'm very happy to incorporate it to make these repair times more useful. Until then, you can still make use of the individual repair times that are available for each component, and perhaps make use of those times to test your own method for sequencing and see how that works. I will talk a little bit more about this tomorrow when I introduce Pelicun and all the details of the outputs that it provides. I will stop here with some exercises. These are just to help you test out the different functionalities that were mentioned today in the presentation. I thank you for your attention. I don't know, Matt, if some other questions came up, I'm very happy to answer. Or if you have questions later during the day, I encourage you to come to the office hours at 2 p.m.
Thank you, Adam. We're up against the end of our hour, so we do want to go ahead and end this, but I want to say thank you on behalf of the attendees for the presentation and the information you provided. To the participants, thank you for attending, and we invite you to join us back for day 3 of the PBE application tool training tomorrow. And so thank you very much, Adam, and this concludes today's webinar.
Thank you.